Okay students, let's do our third problem in Newton's law. So this will be a problem regarding resolution of a force into its components. So we learn how to resolve a force into its various components. Let's read the question and then understand the figure from the question. It has been said that a small block of mass m is resting on a frictionless, smooth, horizontal table. At a moment t equal to 0, a force F equal to kt squared is applied on the body where k is a constant. F forms an angle theta with the horizontal. Find the velocity of the body when it breaks off the horizontal plane and the distance the body covered just before it breaks off the plane. So, let us consider the horizontal plane to be this plane and a body of mass m is resting on it. A force is applied, let this be the applied force indicated by the arrow, and the force forms an angle theta with the horizontal. So this is a horizontal direction, the force forms an angle theta with the horizontal. Now let us find out what are the forces acting on this body. So if I redraw this, this is a horizontal plane, this is a horizontal plane, and my mass m is resting on it. Now if a force F acts on it, making an angle theta, then the force can be resolved into two components. One, which is the horizontal component, which is F of cos theta, and a vertical component here, which is F of sin theta. So why is this? The force is at an angle theta with the horizontal. So when it makes an angle theta, the direction of the force which is along this theta will have cos theta component, and the perpendicular direction will have a sin theta component. Now suppose I consider the other forces acting on the block. That will be the mass mg of the block acting downward, and this table will give a reaction force to the block which acts vertically upward, which I denote as R. R is a reaction force. So let us first see how we calculate 1. That is the velocity of the body when it breaks off the horizontal plane. Before that, let me just write down that what will be my forces according to this free body diagram. So the force acting downward is mg, which will be balanced by the upward force. So since the body has no vertical motion, since the body has no vertical motion, we can say net upward force acting on the body is equal to the net downward force on the body. So what is a net upward force? We see R is one net upward force plus F sine theta is along the upward direction. So both R and F in the same direction, so we'll add them up, and that should be equal to the downward force. So what is the downward force? Mg is the downward force. So this will be equal to mg. Now when the body is breaking off, when the velocity, when it breaks off the horizontal plane, breaks off means what? It moves off the horizontal plane. So when it moves off, the reaction force becomes zero because there's no table pushing it up in the upward direction. There's no reaction force from the table. Since it is breaking off this plane, it is breaking off the table, there is no reaction force from the table, so R becomes equal to 0. When the body breaks off, R goes to 0. So at that time, F sine theta is equal to mg. F sine theta becomes equal to mg. So I can write from this, I can write F is equal to mg by sine of theta. So F is now supposed to be kt squared. From this condition, F equal to kt squared, if I put this, kt squared becomes mg by sine theta, and my t squared, so I can write, this implies t squared is equal to mg by k sine theta. Now what do I have to find? I have to find the velocity when the body breaks off the horizontal plane. So if suppose the body is moving with an acceleration a in this direction just before it breaks off. Suppose the body is moving with an acceleration in this direction. So who is supplying this acceleration? The horizontal component of the force. This force, horizontal component, is applying this acceleration. So then F cos theta will be equal to ma, which is equal to m dv dt. F cos theta will be ma, which will be equal to dv dt. So if I put the value of F as kt squared, then I have this as kt squared cos theta. So now if I rearrange this equation, let me look at this two equation. Let me bring t up here and keep m and cos theta here. So m by cos theta into k dv will be equal to t squared dt. Now if I integrate, these are constants, so it will go out. Here if I integrate, my v will go, it starts, say, a small block of mass m is resting. So if it is resting, then what happens is my initial velocity is 0 when time was 0. At the initial time it was resting, so both of these will be 0. Now let the velocity when it breaks off the horizontal plane be v. So at that time, what was the value of t? What was the value of t at that time? We get from here. So t would be root over mg by k sine theta, whole root over this. So if I solve this and get m by cos theta into k, v equal to, this will be, I have discussed in the previous that x to the power n dx is equal to x to the power n plus 1 by n plus 1. So if I take this, then this will become t cube by 3 in the limit 0 to root over mg by k sine theta. So this will become mg 1 by 3 outside, mg by k sine theta to the power 3 by 2. So this, from this relation I'll get my velocity. So if I write the velocity, this will become, if I take the constants there, then v will become equal to k cos theta by m by 3 into mg by k sine theta to the power 3 by 2, which brings, this is 1, this is minus 3 by 2. So this becomes 3 by root k. M is 3 by 2 minus 1 is half. So you get a root over m on the top, and you get g to the power 3 by 2, and cos theta, you get cos theta into cos theta divided by sine theta to the power 3 by 2. So you get this very complicated expression, but this is the explanation for it. So we have found out the velocity when it just breaks off the horizontal plane. And what will be the distance covered? What will be the distance covered? So for the distance covered, I have found out velocity. Now if I take this equation, let's start from this equation. So let me rub the portion which has been done. So again it is asking the distance covered before it just breaks off. The distance covered before it just breaks off. So this can be written as I can find an expression here. I can write m dv dt equal to mg by sine theta. I can write this, force is mass into acceleration. I can very well write this, and this is nothing but k t squared. So if I had done the uh, if I had done the integration without taking the limit, then I would have this as this term, nv equal to k t cube by 3 plus c. Now I know the boundary condition. When t was 0, the object was at rest. So this, if I put this value of t here and this value of v here, I get c equal to 0. So this reduces to v equal to k by 3m into t cube. V equal to k by tm into t cube. Now I can take this v as distance covered per unit time, ds dt. So I can write this as 3m t cube. Rearranging, this gives ds equal to k by 3m t cube dt. This gives t cube dt. So if I integrate, I get s equal to k by 3m. Again applying integration over x to the power n, dx is x to the power n plus 1 by n plus 1. So this gives 4, this becomes 4, 3 into 4 is 12 by 12m t to the power 4. This is what I get to be the value of s. Now if I use this expression, then what do I get? T squared is mg by k sine theta. So t to the power 4 will be m squared g squared by k squared sine squared theta. If I put this expression of t to the power 4 here, s becomes k by 12m m squared g squared by k squared sine squared theta. Now k and this cancels, so s becomes mg squared by 12k sine theta. So this is the distance the body covers just before it breaks off. So here I have not put the constant of integration because at time t equal to 0, the distance covered was 0, so c will come as 0. So you can verify this. If you have any queries about the calculation or any doubts, please write in the comment section and I'll get back to you ASAP. I hope you enjoyed this video. Thank you.